The paper is called the free transformer. Think of today's decoder transformers as tightrope walkers. They make one tiny step, token at a time, with no chance to set a bigger plan first. The free transformer gives the model a free extra move, a latent variable, chosen before or alongside token generation. That latent can stand for big picture stuff. Topic, sentiment, style, strategy. Instead of hoping those choices emerge implicitly from local token-by-token probabilities, the model explicitly conditions on a learned, hidden code. The result? Generation that can reflect coherent, global decisions while still doing standard autoregressive decoding. The promise here is practical. You keep the familiar transformer machinery, but add a lightweight, unsupervised way to inject high-level structure into the process. It's like giving the model a storyboard before it writes the script. Here's the key move. Introduce random latent variables that the model conditions on and learn them without labels using a variational objective. In practice, that means the model learns an internal code that summarizes global aspects of the sequence, the kind of choices humans make implicitly before they start writing. During training, an auxiliary network learns to infer this code from examples. During generation, you sample or predict that code, and the decoder conditions on it while producing tokens. Why this matters? It separates what overall kind of thing am I making from which next word fits. That separation lets the model represent multimodal structure, different valid global choices, cleanly, and improves controllability. The authors claim you get these benefits with modest compute and memory overhead, so it slots into existing pipelines without blowing up cost. Autoregressive decoding has dominated because it's simple and effective. Predict the next token, repeat. But that simplicity also forces the model to hide global decisions inside local probabilities. This paper argues for a richer density model that can still decode autoregressively while explicitly conditioning on high-level latent structure. The goal isn't to replace next token prediction, but to augment it so the model can represent and commit to big-picture choices early, rather than reinventing them at each step. They implement this as a conditional variational autoencoder wrapped around a decoder transformer. Intuition. An encoder network looks at the sequence or the prompt in context and infers a latent code capturing high-level properties. A learned prior predicts what that code should look like given the prompt. The decoder then generates tokens conditioned on both the prompt and the latent. Training uses a standard variational objective to make the inferred code informative while keeping the prior aligned, so you can sample plausible latents at test time. The engineering promise is important. This adds only a small overhead because you're injecting a compact latent and a light encoder/prior, not rebuilding the model. You keep parallelizable attention, the same training recipe, and the same decoding loop, just with a global steering signal added. To show it's not just a toy, they train 1.5B and 8B models from scratch and test across multiple downstream benchmarks. The point of these experiments is scale and generality. If latents help across tasks and sizes, it suggests the approach improves the model's inductive bias, not just a niche metric. In other words, the latent conditioning should translate into better sample quality or controllability without sacrificing the strengths of standard transformers. A decoder transformer models a sequence by chaining conditionals. Each token depends on all previous ones. Generation mirrors that. Choose the next token, append it, repeat. This is powerful, but local. The model never pauses to make a global call like, this will be a formal review with a harsh tone. Instead, it must approximate those global choices indirectly through the next token distribution at every step. That works, but it's like planning a road trip by only deciding the next turn at every intersection. You can get somewhere, but you might wobble, backtrack, or struggle with multimodal destinations. The proposal is to keep the chain intact, but give it a map beforehand. Crucially, standard decoders don't make extra latent decisions. The only stochasticity they sample is the token itself. That means any high-level factor, style, topic, sentiment, structure, has to be encoded implicitly in token probabilities, which is an awkward place to store global intent. It can blur distinct modes, e.g., multiple plausible outlines, and force the model to continually rederive the big picture. By introducing an explicit latent, you let the model commit early, sample or infer the global setting, then generate tokens consistent with it. This tends to sharpen modes, improve coherence, and make control more natural. Take movie reviews. A plain decoder can generate both positive and negative reviews, but it never explicitly decides which one it's writing. It just nudges token probabilities as it goes, slowly drifting toward one tone. That's workable, yet brittle. It can mix tones, flip late, or require careful prompting to steer. With a latent variable, you can represent sentiment as a global switch. During generation, sampling or setting that latent commits the model to a positive or negative trajectory from the start. Two benefits fall out. Modeling. The distribution becomes a clear mixture of modes rather than a muddled compromise. And control. You can reliably steer output by choosing the latent without micromanaging every token. Yes, by the chain rule, any distribution can be written autoregressively, but learnability and efficiency matter. For multimodal data, a pure autoregressive factorization often smears distinct modes across token steps, making training harder and samples less coherent. Explicit latents act like labels you don't have. They carve the space into clean, high-level choices that the decoder can condition on. That inductive bias can reduce perplexity, improve consistency, and make control easy, even though, in principle, a huge enough AR model could simulate it. The argument isn't about possibility. It's about giving the model the right knobs so it learns the structure we want, with less struggle.